Hi everyone and welcome to this new video of Data Science at Scale with VerticaPy. It's Badr speaking. In this video we will understand the concept that is used more often because of its business application: real-time and near real-time analytics. Different data science projects have different time constraints. Sometimes it is needed to act fast in order to avoid the worst. But for many use cases we don't need an instant response. Does real-time really exist? When to do real-time or near real-time? What type of data preparation we need in order to deploy our work? We will answer to all those questions. But first, let's consider the following situation. Two automated cars are taking decisions based on the environment. They have to drive safely in order to avoid any collision. The situation can become quickly very dangerous when the security distance is not respected. If the autonomous car has to query the database, it can be risky. Indeed, if the signal does not come on time, the risk can become huge and the worst can happen. Near real-time response may be not enough for this use case. Our room to maneuver is quite limited. That's why it is important to implement the solution directly in the car itself. The autonomous car can then do some computations using a pipeline machine learning object and take action. But most of the time, we don't need a real-time response. Near real-time is enough. Credit card fraud detection is an example. A fraudster could have stolen a credit card. He can try to withdraw a huge amount in the ATM machine. The machine can query the database to look at historical data. It uses in-database computations to do the scoring and send back the result. The fraud can be identified quickly enough to send the alert. Few seconds are enough to take action. This is what we call near real-time. Depending on the implementation, use cases will be solved differently. Sometimes we have much more time to take action. When a customer is complaining to a telco operator, it can be a signal for churn. The call center can put on hold the customer for a short period of time. It does not need a second time response. Many computations could possibly happen before taking action. We can then define three categories for the different use cases. Real-time use cases need a fast response. We don't have access to historical data and we need to pre-process and score the data quickly. Car accident prevention can only happen if a car can quickly stop when the danger is detected. The concept exists, but its application is not really feasible as signals need time. Most of the time we consider real-time as a milliseconds response. But not all use cases need a very strict response time. In near real-time use cases we have to act quickly to head the business. It can be 5, 10 seconds or even some minutes. The data can be in database and some sophisticated data preparation techniques can be used, as long as it is fast enough. For example, an ATM machine can take few seconds before allowing a withdrawal. If a use case has no time constraint, we are free to proceed the way we want. We can even use expensive techniques. An example could be to understand which customers are churning to take action later. There is no need to act now. Let's see the algorithms that can be used for different categories. Many different algorithms can be used in all use cases. Real-time, near real-time, and without any time constraint. This list is non-exhaustive and can help you to understand what kind of techniques you should use for real-time use cases. I really recommend k-means clustering, isolation forest, and basic rules and threshold because of their simplicity of deployment and because of their nature. Robust PCA and most of the ensemble techniques can also be used in all kinds of use cases. However, depending on the number of trees and their depth for ensemble methods and the number of components for robust PCA, the computations can be expensive. That's why we need to be careful when trying to use this model for real-time use cases. Most expensive techniques could be harder to deploy. That's why dbScan clustering or local outlier factor cannot be used for real-time or near real-time use cases. Indeed, as they are based on some neighbors or density computations, Their deployment can be very hard and expensive to achieve. Wow! You now know the difference between real-time and near real-time. To understand more deeply the concept, it is important to do some hands-on. We will use Jupyter and VerticaPy to create two models that can be used in both cases. We will see how: creating a database connection, ingesting a dataset, preparing relevant features, creating two machine learning models, one for real-time and another for near real-time use cases. Let's go! Let's use Jupyter Notebook to illustrate this topic. You can click on the link to download the dataset in Kaggle. An entire study of this dataset is done in another video. We will be more focused in the real-time, near real-time concepts. Let's import the VerticaPy package and its SQL extension. If you did not create a permanent connection, those lines of code will allow to save the credentials in the VerticaPy directory. Be sure to have the same or an upper version to avoid compatibility issues. For this use case, let's create a new schema. We will name it Credit Card Fraud. We can ingest the dataset using read CSV. It will use flex table to identify the different data types and store the dataset in the Vertica database. This dataset includes many transactions, and we have access to the card ID, the date of the transaction, the amount, and if the transaction is a fraud. We can build many interesting features, as there is a chronology and we have access to an ID, a date, and an amount. An ID is to compute the Z-score for each different credit card. We can also compute the number of seconds elapsed since the last transaction. If it is the first transaction, we can impute the value using plus infinity, which is represented by the maximum value. Extracting the hour of a day can also be a good idea. We can expect that many fraudulent transactions will happen at specific time. We can use moving windows to count the number of transactions and its average amount in the last 30 minutes. Moving windows are very interesting features which can catch relevant temporal information. We are looking just before the operation how many times the card was used and what was the average amount. Let's create a machine learning model. Let's convert the response to integer. Import the Random Forest Classifier and seed the randomness. It is needed to get the same notebook results. Be careful when seeding the randomness in the context of big data. MPP columnar databases like Vertica don't like indexes. They will slow down the operations. We can then split our dataset into train and test, create a random forest object with customized parameters. We are also providing a name to the object as it will be stored in the database. Feed the model. For near real-time use cases, we have access to historical data. We can query the database and we can use sophisticated features like advanced analytical features and moving windows. Let's compute the AUC. Wow, an AUC of 86% for a first shot. It's not bad at all. When doing near real-time, we can use the predict method of a vdata frame to do directly the predictions in database. It is a little bit different when doing real-time. We don't have access to historical data. Only easy computable features like the hour and the amount can be used. The score will drastically go down because of the limitations, only 71%. It is impossible to export our model to independent Python code. The VerticaPy function to Python will help to export our models. We can bring the model directly in the system to do the scoring. For example, transaction of $3,000 at 2 a.m. will raise an alert. VerticaPy allows to solve use cases with different time constraints. It is possible to do in-database scoring or to export the model out. It is then easy to solve any kind of use cases with few lines of code. Thank you for watching this video. If you liked it, subscribe to the VerticaPy channel in LinkedIn. Visit our GitHub page and add a star to the project. Learn more by visiting our website at vertica.com/python. You can also subscribe to our YouTube channel. See you soon for another video.